Hi, good day. I'm continuing the presentation on machine learning, data science, NLP, and big data. And this is the second section. I'm Tiniam V. Ganesh, and I'm going to be talking about logistic regression. This is another type of supervised learning, except in this case, we are not trying to use input variables and features against continuous response. Rather, we are going to use input features against discrete responses. That is, we are trying to classify the response as one of many. So, for example, given a tumor size, can we predict whether the tumor is benign or cancerous? So that's actually just a benign or a cancerous possibility, or whether an email is spam or not. Maybe whether a financial transaction is fraud or not. So really, we're really trying to trying to classify a given domain into multiple levels. It's not discrete and it's not continuous. Rather, it's discrete, and it can have one of many levels. So essentially what we are trying to do is, for example, whether an email is spam or not spam, we need to be able to have a 0 or a 1. It should be a binary kind of an output, where your output should predict either a 0 if it is not spam, or 1 if it is actually spam. And fortunately, there's a very interesting mathematical function known as the sigmoid function, or the logistic function, which is shown here. Basically, if you look at this function, the function, when it is positive, for z greater than 0, it quickly asymptotes to 1, and for z less than 0, it quickly asymptotes to the value 0. So we use this function in trying to classify a particular regression problem into one of two possibilities, either a 1 or a 0. So let us see how that is done. And that is done typically by the use of this sigmoid function. So for example, again we choose a parametric form for the hypothesis, which is, we could say it's of the type of beta 0 plus beta 1x. But since we need this response to be between 0 and 1, we specify the hypothesis function, or the estimate, to be of the form of this logistic function, which is 1 by 1 plus e power minus beta 0 plus beta 1x. So this particular function can really only take one of two values. So when it's greater than 0, it asymptotes to 1, and when it's much less than 0, it quickly asymptotes to 0, as we've seen in the previous slide. So when y is greater than 0.5, z, so this is what we try to do. So here, for example, if we assume our estimate to be of the form to be beta transpose x, where this is the parametric version of our decision line, then the estimate is of this form of this sigmoid function. So when this a parametric form beta transpose x is greater than 0, it asymptotes to 1, and when it's less than 0, it quickly asymptotes to 0. So we get one of two values. But again, just like in the linear regression, where we had continuous values, we had determined what is known as the mean square error, or the cost function, which essentially tries to make the cost high when our prediction is wrong. That is, we try to minimize the cost. That is where in the previous case, we assumed the cost was the difference between our actual data and our estimated data, the square of the sum of the distances. So here what we do is, we assume this cost to be of the form minus log the estimated function if y is equal to 1, and minus log 1 minus the estimated function of y is equal to 0. So quickly let us look at this cost function. Why we write the cost function as this? We know that log 0 is 1, minus log 0 is infinity, and minus log 1 is 0. So if our estimate is 1 and y is 1, then minus log 1 is 0. That means our cost is 0. That means we have made a perfect prediction. Whereas if if y is 1 and we are actually predicted for estimate was 0, then minus log 0 is equal to infinity. Similarly, we can actually look at this. If y is equal to 0 and we estimated a 1, then 1 minus 1 is 0. So log 0 is infinity. That means it's a poor prediction. Whereas if y is 0 and we actually estimated as 0, then log 1 minus 0 is log 1, which is equal to 0. That is again a perfect prediction. So it's just like in the case of linear regression, we use gradient descent to minimize this cost function, and it can be done with that. So here's an example of this cost of a classification example. So here we have, let us assume that this is the size of the tumor on the x1 axis, and x2 axis is the age of the tumor, and these circles are benign tumors, and these x's are cancerous tumors. If we assume that we use logistic regression and actually solve this, and we got this coefficient vector as minus 3, 1, 1, then essentially this means that beta 0 is minus 3, beta 1 is 1, and beta 2 is 1. So if we substitute it in this equation, it means minus 3 plus x1 into 1 and x2 into 1 is greater than 0. We get this equation. So now when this equation is greater than 0, when this equation is greater than 0, then our logistic function would asymptote to 1, y is equal to 1. So if y is equal to 1 when this is greater than 0, and y is equal to 0 when this is less than 0, and I say y is equal to 1 because 1 plus if I use if I use this left hand side into the as a function of the sigmoid function, when the sigmoid function is greater than 0, then it will asymptote to 1, and when the sigmoid function is less than 0, it will asymptote to 0. Okay, now let us look at neural networks. Actually, neural networks originally started with Frank Rosenblatt with his original implementation of a perceptron, and it was fairly successful and did a great breakthrough in the advancement of a new type of machine learning. The fact that neural network, the advantage of neural networks over other types of regression is that you can actually you don't have to worry about the polynomial order of the input features or the correlated features. So here let us look at a neural network. You have 3 input wires, and you have a computation unit, just a similarly logistic computation unit, and then you have an output. So for example, you have 3 input wires, x1, x2 and x3, and then you have weights which are used on this which are used with this inputs, and then you take so a neural network is a network of many logistic units organized into layers, where each layer output is into the next layer. The very first layer input is the model features x1, x2 and x3. The last layer is the output. This is known as the forward propagation. So here A1 is if you look at it, it takes inputs x1, x2 and x3, and the weights are beta 1, 1, beta 1, 2 and beta 1, 3. So a1 is the logistic function of beta 1 0 plus beta 1 1 x1 plus beta 1 2 x2 and beta 1 3 x3, and a2 is beta 2 0 plus beta 2 1 plus beta 2 2, so on. So similarly, where gz is equal to 1 by 1 plus e power minus z. And finally, fz, that is the estimated function, is dependent on a1, a2 and a3, and beta 1 3, beta 2 3 and beta 3 3, which is what I've written here. So this is how we compute this estimated output depending upon the inputs and the weights. So here this middle layer is known as the hidden layer, this is known as the input layer, this is known as the output layer. And neural networks are very good at determining nonlinear boundaries also. So here in this case, here we have, if we take a neural network with two inputs and a bias input x1 and x2, we can show that we can, so here I've shown, this is, you can assume that when x1 is between 0 and this one, it is 0, and when x1 is greater than this as 1, and again when x2 is below this, it is 0, and x2 is above this numerical value, it is 1. So here if you had let's say this is a cancerous and a non-cancerous depiction of depending on these age and tumor size, and if we actually got data like this, then you will actually have to create a decision boundary which separates this like this, and this is a non-linear decision boundary. But you look at it, it's actually like an XOR function. So this region is 0 for x1 and x2, and this above this it is 1. So for both 0 0 and 1 1 it is 1, and for when either x2 is 1 and x1 is 0, or when x1 is 1 and x2 is 0, it is 0. So it is 0. So we can assume that that is the way it is. And we can use neural networks to determine this particular boundary. We'll see how that is done. So for example, we can simulate Boolean gates with neural networks. So for example, if we assume that we had got weights minus 30, 20 and 20, and we had inputs x1 and x2, then this actually simulates an AND gate. Okay, so what this means is, if x1 was 0 and x2 was 0, then only you get the bias input, that is minus 30. So g of minus 30, a large negative number, you see it asymptoted to 0. When one of it is 1, when x2 is 1, it is g of minus 30 plus 20, which is g of minus 10, which is again 0. But if both were 1, then it is g of minus 30 plus 20 plus 20, which works out to g of 10, which is a positive number, which means it will asymptote to 1. Similarly, here this is a NOT gate. When the way the bias unit is 10 and the input unit is minus 20, so when x is 0, then this has no effect. So g of 10 is 1 because it's a positive number, and when x is 1, then it is g of 10 minus 20, which is g of minus 10, which is 0. So similarly, you can use a complex combination of neural network using an AND and a NOT and an OR gate. You can combine them to actually do an XOR X2 realization. So this is an AND gate, which I have shown in this red. This is a NOT X1 and NOT X2, which is this one, and finally the OR gate. If I combine this, I actually get an output which is a XOR gate, which is what we get this, what this problem was. So you can use networks to create nonlinear decision boundaries. And then you can have multi-layer hidden neural networks, where you have one input layer and multiple hidden layers and an output layer. So what we saw, this is known as a feed forwarded, because you have input and you keep feeding it forward, it goes all the way right to the output. But you have another technique known as back propagation, which basically takes the output from your network and compares it with the real value of that y, real output value, and calculates the error. And then using it takes the derivative of the error and feeds that partial derivative of the errors to the preceding layers and tries to correct the actual input. It tries to correct all the weights based on the error between the actual output and the estimated output, and thus the neural network actually corrects itself and ensures that the predictions are much more accurate. That's why we say neural network is capable of learning. Now let us look at variable selection techniques. We saw in the earlier example where in the advertising that newspaper did not influence the sales of the product as much as, in fact, it didn't influence it at all, whereas TV and radio advertisement significantly improved the sales of the product. We determined that it was not required because it had a very high p-value. There's another way of determining which variables are actually important in the actual response, and one of that is known as the forward selection. In the forward selection, we begin with the null model. That is, we start with the model which has no inputs or no features or no input predictors, and then we take each of the each of the input variables or predictors one by one to the null model, and then add that input variable that results in the lowest residual sum of square, that is the lowest error. You add one by one each of these predictors, and you find which one gives the lowest error when you add each of these input variables one by one, and then you pick the one which has the one. Then the next step is you take two input combinations of two input variables, that is let's say x1, x2, x2, x3, x3, x4, and again you determine which of that gives the smallest error. So now you have a combination of a single input variable and then combination of two input variables. Similarly, you do that for 3 and 4, and you add it up to p. And essentially what they're claiming is that that is probably the best set of input variables you can have. The second technique is known as backward selection. We start with all the input variables in the model, and then we remove the variable with the highest p-value, because in the case of newspaper and TV and radio, we saw the newspaper highest, we remove that. Then we take the next highest then we take one variable, combination of one variable less, and then we remove the one with the largest p-value. Similarly, we do that. So essentially what again this is doing is trying to find the sets of input variables that would result in the best model. And then there's a combination of both forward and backward known as mixed selection. There are other machine learning methods. One is the ridge regression, which is also known as regularization. So ridge regression, instead of doing this forward selection and determining or the backward selection and finding out which combinations make this best sense, the ridge regression, what it does is, besides computing the mean square error, here the residual sum of squares is the estimated output response, not the real response, minus the estimated response. That is beta 0 minus sigma of beta j xij. This is just that what you already seen, the mean square error, not mean square. Mean square you would have had the n minus 2 denominator, but this is just the residual sum of squares. This is the estimated function the real data value minus the estimated function the whole square. And here you add a new term known as lambda sigma. For each of those coefficients we add a beta 1 square plus beta 2 square beta 3 square, and then we use gradient descent or some regression method to minimize this composite function, and we change these values of lambda. And typically this lambda is known as a tuning parameter, and essentially what it does is it shrinks or reduces the effect of some of the parameters close to zero, or in other words it makes the effect of some of the predictors almost close to zero. So if we had used this in that sales and TV and the advertising budget for the various channels, TV, radio and newspaper versus the number of products sold, if we had used this, instead of even looking at the p-value, you would find that for the newspaper, the coefficient for the newspaper beta 2 would have almost come close to zero, or which means that it would show that it has no effect. It will automatically do that for you. The second method is known as Lasso. While rigid regression does bring several of the input features or predictors close to zero, it doesn't exactly make them zero. And they continue to have a small, a finite but very small coefficient. Rather, the other option is to use the lasso, which will shrink some of the coefficients to zero. I mean, not close to zero, just make them zero, and it's supposed to be much more effective. There are other models known as, for example, the regression splines. So for example, if you had data like this, spread like this, instead of trying to fit one nonlinear curve over the entire region, we try to specify this response as a sum of different polynomial functions. So from this region to this region we use one polynomial function, this we use another polynomial function. It's known as piecewise linear functions, piecewise polynomial regression. But obviously if you look at this is not a good solution, because there's a discontinuity at the age of 50. I mean, if you remember the discontinuity, it means the left hand side is not equal to the right, and the derivative of the left hand side is not equal. Whereas an alternate, this one here, it is actually equal. So there are mathematical methods to make it continuous at these knots. These are called knots, where these two different polynomial functions actually join. So there's a mathematical way to make it first order continuous and second order continuous. Then there's another model known as k nearest neighbors, and the way that is done is you take for k training observations that are closest to x0 are taken, and then the average of the response is considered. So you take a region, you take n number, maybe n is equal to 5 or 10. Depending on the number you take, it will either overfit or underfit. If you take let's say k is equal to 5, you take the 5 closest points, and then you take the average of that point and assume that your estimated function is there. You take the next 5 points, and then you take the average of that, and you assume the estimated function is there. So that's how you compute your estimated function, by taking sets of data, averaging them out, and essentially saying that's your estimate function. Then there's another one known as generalized additive models. So here, instead of saying y is a linear function of the different input variables, here you take beta 0 plus each of the feature, you assume it is a function. You assume that x1 is a function of x1, x1 i2 is a function of another function of xi2. So it is an additive function. Okay, now let us look at some of the important issues that occur when we are trying to do this regression. So for example, if we had there are two important considerations which you have to take when doing machine learning. The first is bias and the second is variance. When we have data like this and we try to fit a linear a linear regression, then this is known as an underfit, because it doesn't do a very good job of trying to generalize this function. Whereas and it's known as an underfit, or it's known as to be heavily biased. Whereas if you look on the right, here we use a higher order functions, and it almost does it too well. In fact, it kind of very squiggly and goes over all through all the points. Oh, again, this is again not a good generalization. This is known as overfitting. Whereas this here you use a second order polynomial and it is just right. When a data set is given, typically we split the data into training and test set. We make 80% as our training set and 20% as our holdout set. And the reason we do that is, if we use some machine learning algorithm on the entire 100%, then the algorithm will tend to learn what is already so if we split it as, if we use the entire 100%, then it will fit the 100% data very well and will not fit on new data. So rather what is done is you take a random sample, about 80% of the data, and you train your model on the 80% of the data, and then you test it on the remaining 20%. If it fits the remaining 20% well, then you can say that you have been able to generalize the data very well and you have got a very good model. And this is known as cross validation, and it's typically used. In fact, they go one step further, and what they do is they split it into 60% training data, 20% cross validation data, and final 20% as test data. So you train the model on 60%, then you keep trying out, you keep refining your model and test it against the cross validation data, and you try to minimize, try out different models and try to get the lowest error. You get the best fit on the cross validation data, and once you are fairly confident that you've got the best fit, you then try to use it on your test data. It should do pretty well on the test data. There are multiple cross validation techniques. The first is leave out one cross validation. A single observation x1 y1 is used for the validation set. So what happens is you have x1 x2 up to xn. You train a model from on all the other data x1 x2 y2 all the way up to xn yn, and then you test the model on the remaining x1 y1. So you do random combinations of this, and you try to find a model which will minimize the error. The other one is known as k-fold cross validation. So here you randomly divide your data into k groups or folds. The first fold is treated as validation, and the method is to fit on the remaining k minus 1 folds. So you keep doing that k times, and you take the average of the mean squared error. That's your cross validation error, and so that way you ensure that your model is being refined. Now let's look at some of the issues that come up with degree of polynomial. So when you start off, as I said, if you go for just a linear equation, beta 0x plus beta 1x, beta 0 plus beta 1 x1 plus beta 2 x2, then you're going to get a straight line, and that is going to result in a underfit, as we saw here, underfit, and it is going to also give a very big error, high bias error. But as you increase the order of the polynomial, you make it quadratic, cubic, and it'll fit the data points better and better. In fact, as you increase the degree of the polynomial, it'll do so well that your training error will come very low, but actually the line will tend to become very squiggly, and it will not generalize. So while it will fit your training data well, but if you test on the models against the cross-validation, initially for a first order equation, you will get a high cross-validation error. That means it won't fit even the validation data. But as you increase the order of the polynomial, the fit will be generating better and better, and then it will come to its minimum. And as you further from this point, as you increase the degree of the polynomial, the training error will go down, but your cross-validation error will keep going up. So what this essentially implies is that your best model was when you had a degree of polynomial whatever corresponded to this point, and it was the lowest cross-validation error. So again, this regularization which we saw in the regularization and the lasso, what happens is when there's a small lambda, you tend to overfit, and for a large lambda, what happens is it would make some of them zero generalized well, it would underfit, and the cross validation error for small lambda would be very high because the cross validation will be very high, and as you are increasing the lambda, your error will keep coming down, cross validation error, and then you'll reach a point where it will reach the minimum, and then it will start again for a very large lambda, it will start increasing again. Normal neural networks have one or two hidden layers used for supervised prediction. Deep learning differ from non-learning because they have more hidden layers. Deep learning networks differ from. Actually, deep learning can also be used can be trained in an unsupervised or a supervised manner for both supervised and unsupervised tasks. In supervised neural networks, we predict a target Y from a matrix of inputs X. Taking an input, an unsupervised neural network, you can predict the matrix X using the very same matrix. You can predict the input using the same input to learn from. Here's some of the trade-offs. What this shows is this model. There are different models of machine learning, and each of it are best suited for different purposes, and there are pros and cons of it. So if you look at the least squares, that is your what we saw was your linear regression of the gradient descent. Typically, it is very flexible, and it is also highly interpretable. The lasso is highly interpretable because many of the predictors would be actually zero, but it is not very flexible. So you cannot do not very flexible. The support vector machines are very flexible in that you can do a lot of you can use it to fit different combinations of input data, but they're not very interpretable. So we come next now to the unsupervised learning. What is unsupervised learning? Unsupervised learning is basically where you just have data, you don't have a response, and you are trying to understand something about the data. So basically we use something known as clustering, is learning from the unlabeled data. So if I had data like this, here I've shown balls faced, runs scored, and minutes in the crease of Tendulkar, and if we have plotted the data like this, then I can actually use a method known as k-means clustering and find out the three clusters that are there for these data points. When is supervised learning used? Supervised is used in market segmentation, trying to find how different groups of people behave, in social network analysis, in understanding galaxies, whether there's some galaxy being formed, whether you see a pattern in that, it's used there, and so on. So essentially we have covered a lot of topics. We have covered regression, linear regression, where we used the mean square error, which is essentially the square error, between the actual response and the estimated response, the square of that, and we take the mean of that, and we try to minimize that using gradient descent. And secondly, we looked at logistic regression, where we try to classify the output into one of two possibilities, either a 0 or 1, and we used what is known as the sigmoid function. Then we looked at neural networks, which can be used for far more complicated nonlinear decision boundaries. And fourth, we looked at deep learning networks. Thanks.